Okay. Good morning, everyone, and thanks for giving me this opportunity. And today I'm going to be talking about dark energy instabilities induced by gravitational waves. And this work I have collaborated with Paolo Cleminali, Giovanni Tambalo, and Filippo Vinizzi. Okay, so let's get started. So it has been quite some time that our universe today is in the phase of accelerated expansion. And of course, the simplest solution is to use the cosmological constant. And that you have to deal with the cosmological constant problem. And many people have been trying to build up a model of dark energies. For example, you can have the quintessence, PRX, and so on. And recently, we have detected the gravitational wave signal coming from a binary system. And this opened up the test for theory of gravity and all those modified gravity theories. Okay. And the idea of this talk is to use the gravitational wave propagation to constrain those dark energy models. Okay. So first, I would like to give you a review of a dark energy model in the context of scalar-tensor theories. Okay. So the simplest model is the so-called quintessence, where you have the minimal coupled scalar field with a gravity. And then you can have a non-minimal coupled scalar field with a gravity. And this is a so-called branch decay model. And then you can have an arbitrary function of a scalar field and its kinetic x. And this is the KS. Here, I would like to point out some interesting features which typically happens in case of P of X. So for example, if you perturb around a cosmological background phi 0 of T, then you have this fluctuation pi. Okay. Then you're going to see that this pi wave will acquire a sound speed Cs. Okay. And it means that this pi wave will travel at a speed which is typically different from the speed of light. Okay. And here I'm showing you the most general scalar tensor theories where you have the second order differential equation, and this is a so-called Horndeski theory. Here for Horndeski, you have four functions, G2, G3, G4, and G5. For beyond Horndeski, you have F4 and F5. Many people have studied these theories in many contexts, in many aspects, like black holes, gravitational wave, and so on. Here, I would like to point out some interesting phenomenon. So for example, if you consider this term phi mu nu, the square of the second derivative acting on the scalar field, then you do the perturbation around phi 0, which basically breaks Lorentz invariance. Then you're going to see that the tensor perturbation gamma ij, which is our gravitational wave, will have a sound speed ct. And this ct generally is different from the speed of light. And using this, we're going to constrain this model of dark energy. So I would like to move to another language of explaining dark energy models. And this is the effective field theory of dark energy. It's just an efficient way to study a perturbation around a fixed background, which is the flat FRW metric in this case. So the idea is that you're gonna write down all the terms which are compatible to the three-dimensional diffeomorphism. So you see that this Lagrangian can be a function of time, lapse function, extrinsic curvature, and the Ricci scalar of the surface. Okay, and it turns out that for a dark energy model, you can write down all of these terms. Okay, it's very complicated. So I'm going to explain line by line. So the first line is governed by the background evolution of the universe, and the second line start at second order in perturbation, and the third line start at third order in perturbations. Okay. So here I would like to point out some this operator M4 square, okay, with this delta K2. Okay, this is a definition of delta K2. And this term essentially contains gamma ij dot square. So this means that this operator M4 will contribute to the sound speed Ct, the speed of the gravitational wave. And actually in 2017, we have detected the gravitational wave coming from the neutron-star merger. And after that merger, we have gamma ray emission, okay, after the merger 2 seconds. Okay. And this 2-second difference is telling you that the sound speed, the speed of the gravitational wave is different from speed of light by 10 to the minus 15. Okay, and using this constraint is telling you that this M4 operator has to be less than 10 to the minus 15. Or you can even set, if you want the theory to have the Ct to be unity, then you're gonna set this M4 to be equal to 0. So this reduces a huge, large class of the dark energy models. So basically, we are left with this Lagrangian. We have a background M2, M3, and M4 tilde. Okay. So now I would like to move to another interesting phenomenon, which is the decay of the gravitational wave. So let me tell you that the decay of the massless particle is allowed in the Lorentz violating theory, okay, but it's not allowed in the Lorentz invariance theory, okay. So here I'm considering the M4 tilde operator like this, which is corresponding to beyond Horndeski, and one can extract the interaction from this operator gamma ij double dot di pi dj pi. And this interaction is surpassed by a scale lambda star, which is proportional to lambda 3. Okay, lambda 3 is a typical cutoff for the EFT. Then you have this alpha h, which parameterizes the M4 tilde operator. Then from this interaction, you can easily compute the decay rate, the perturbative decay rate, which is proportional to omega to the 7 by dimensional analysis. Then we plug in the frequency at LIGO and Virgo, which is around 10 to the minus 13 eV. Then you compare this decay rate with the Hubble. Okay, so you see that this ratio is proportional to 10 to the 20 alpha h square. Okay, and since we have not detected the decay of the gravitational wave at LIGO and Virgo frequency, so we're gonna require that this ratio has to be less than 1. So that means that this alpha h is less than 10 to the minus 10. So this means that the beyond Horndeski theory is highly constrained by a perturbative decay. But notice that so far we have only considered a decay of a single graviton. But in reality, that the gravitational wave from the binary system is not just a single graviton, but is a correction of the gravitons. So one has to take into account the effect of a large occupation number of gravitational waves, and this leads to some non-perturbative effect of pi production. Okay, so let me remind you that after imposing this constraint Ct equal to 1, we have this we have this background, we have this M3 operator, and also we have this M4 tilde operator. And this M4 tilde is highly constrained by perturbative decay. Okay. So now I'm going to be focusing on the M3 operators, which basically you can extract this interaction between gamma and dark energies. Okay. And it's suppressed by the scale lambda. And this scale lambda is essentially proportional to what we call lambda 2. And lambda 2 is 10 order of magnitude larger than lambda 3. Okay. And now we're going to treat the gravitational wave as a classical background in this form, sine wave. Then you plug this back into the action. Then you see that the Lagrangian for pi will become like this. So you have the 1 minus beta in the spatial derivative. So you see that also this beta is a dimensionless parameter, okay, proportional to the amplitude of the gravitational wave. So you see that if beta is less than 1, okay, you're going to have the so-called resonant instability. This was studied in this paper, okay, and it turns out that in this case, beta less than 1, we can improve about on alpha h, but whereas it's not applicable for the M3 operator due to the nonlinear self-couplings, okay. Anyway, so here, if beta is larger than 1, what happened? What happened is that this term can flip aside, and then it gives you the so-called gradient instability. So here I am interested in this case where beta is larger than 1. Okay. So let me just remind you that here we have this Lagrangian of pi, and in principle you can have the nonlinear self-couplings, and also you can have a source terms. So in general, if beta is larger than 1, it will lead to this, the gradient instability. But the question is that, can the nonlinearity stop the instability? And also we have to we want to consider the instability of the background of pi induced by the gravitational wave. Okay. So let me just consider a generic Lagrangian for pi field. Okay. So suppose you have this Lagrangian of pi, and then you do a perturbation around pi hat, which is a background of pi. Then you have the z mu nu, the kinetic matrix for delta pi. Delta pi is a fluctuation around this background pi hat. So it turns out that if you want the theory to be healthy, okay, free of any instability, you gotta impose conditions on this kinetic matrix z mu nu. And it turns out that for the absence of ghost instability, you have to require that z00 larger than 0. And for the absence of gradient instability, you have to require that this combination has to be positive definite. And it has been studied in this paper by Nicholis and Ratazzi that in the case of cubic Galilean, in the absence of gravitational wave, there is no ghost or gradient instability for non-relativistic source. But here we are studying the instability of pi in the presence of the gravitational wave gamma ij. And here you have the kinetic term, and then you have the self-couplings, okay? And then you have the interaction between gamma and pi, then you have a source term. So it turns out that you can read off the expression for the kinetic matrix z mu nu, okay, into this. So this term is coming from the quadratic action, and this term is coming from the self-coupling, and this red one is coming from the interactions, gamma pi pi. And then you have this curly k mu nu, which is proportional to the second derivative acting on pi hat. Then the equation of motion for pi hat is given by this way. So this blue term is coming from the self-coupling, the red one is coming from the decaying term, and then the green one is a source term. Okay, and it turns out that when we assume that this gravitational wave gamma mu nu is in the u direction. U is the t minus z. Okay, then you can solve this equation of motion analytically. We can explain this pi double prime in terms of gamma dot squared with a plus minus sign, sorry. Okay, and then you can explain all the components of z mu nu. Okay, you have the z 0, 0, 0, 3, 3, 3, 1, 1, and 2, 2. So now I would like to give you some impression of what is happening. So remember that to have for the absence of gauge instability, we require that z00 larger than 0, right? But in this case, on the other hand, this case, so here, if you plug in the expression of pi double prime here, so you have a minus sign here, and then you have gamma dot square. And gamma dot square, remember, is essentially beta square. And in our case, beta is larger than 1. So you have this, since you have this minus sign, then it might be that this z00 will flip sign and it becomes less than 0. And this will give you the gauge instability. And in the same way for z11. So this gamma dot 11 is proportional to beta. And then when beta is larger than 1, it flips the sign of z11 to be positive. Then it gives you as well the gradient instability. Okay, so here I'm reminding you that for absence of gradient, we require that beta is less than 1 from these conditions. And then for the absence of gauge, we require this condition on beta as a function of Cs. And this is coming from z00 being larger than 1. Here is a plot between alpha b and Cs for LIGO and Virgo frequency. And this blue region is where our frequency is larger than the unitary cutoff. The yellow region is where there is no gauge, and the green one is where there is no gradient. So essentially, if you want the theory to be healthy, you have to require that alpha b is less than 10 to the minus 2. So in this way, we put a bound on the cubic Horndeski theory. Okay, and the next question would be what happened to the instability? Okay, so essentially when the instability occurs, the fluctuation pi will grow at the rate of the cutoff, and then what will happen is relies crucially on the UV completion, also the fate of the gravitational wave gamma mu nu. But here I would like to give you some feeling that it might be that the UV completion will kill the theory, in the sense that suppose in the IR you have P of X, and in the constant X background, if you go to some certain limit, certain direction in the field space, then you will encounter the gauge and gradient instability. But it turns out that this instability can be cured in the UV, since the UV theory is just a single scalar field with a Mexican hat. And we know that all the modes in the UV are stable. So this means that the instability in the IR, it's just a signal that we need a UV completion, okay, to fully explain physics. Okay. And so now let me just summarize. So we have studied perturbative and resonant decays of gravitational wave, and then this gave us a bound on quartic beyond Horndeski of H. And then we study the gauge and gradient instability of pi in the presence of the gravitational wave, and then this gives us the bound on cubic Horndeski. And here is the surviving Scalar-tensor theory for dark energy, okay, after performing the conformal transformation. Okay. So, and then the fate of instability crucially relies on the detail of the UV completion, which is not known for EFT of dark energy. Okay, so that's it of what I wanted to present, and thank you for your pay attention. Thank you.